algorithms, which are just designed to limit the number of times a certain area in memory is rewritten so that the device doesn't wear down as much. They might decide to remap the memory where your file was to some other place. So you might still have that file, bits of it, saved on your flash drive in a way that's just been programmatically disabled by your flash drive controller. So someone could come in there and still extract it later on. And if you want to do some more active approaches to these kinds of attacks, you can actually just inject faults. So when you're writing a program and stuff, you don't expect anyone to be messing around with the voltage of your CPU registers or anything like that while the program's running. You can't really predict that. This means that even if you have code and you say there's absolutely no security vulnerabilities in this, if you don't consider the entire system, someone could just come in there and hack your hardware. And so your software security doesn't mean anything if they can do that. You have to consider the entire system. So things you can do like this are just put a probe on there, zap it with extra voltage or decrease the voltage. You can change the clock frequency for a bit. And what this can do is you can skip instructions, cause reads or writes to fail, or even execute the wrong instructions. And this can have various bad effects. You can use it to, once again, extract keys from stuff, or just bypass authentication. Like if you do reverse code engineering at all, like a lot of time in these fun key gen things or whatever, you come up with a point where there's like a check, a conditional jump that goes one place if your password was correct, or somewhere else if it wasn't. You just knock it out, and then you can get access to everything. That's basically what you can do here too on the hardware level. And there's another problem we have to talk about, is hardware Trojans. So these days, your devices could be designed in like Silicon Valley, manufactured in China, sold to you from some company in Brazil, and assembled like in Idaho or somewhere. And between the time that they're designed and the time that they get to you, and even after they're in use, how do you know that no one's tampering with them? Well, it's a very difficult problem, and one that the United States Department of Defense is concerned about enough to be writing reports on it. So it's also real because there's lots of counterfeit integrated circuits out there. These things are just designed by people who want a quick buck. So they say this is more like high-end chip that meets all these stringent requirements when it really doesn't, but it still does basically the same thing more or less, hopefully. So these chips, counterfeit, have actually been found in like United States military hardware even. So they can't detect them there, then what hope do we have? If you can get counterfeit integrated circuit chips out there, then who's to say that you can't put a hardware Trojan backdoor in one of them? It's a very real worry. But so far, we actually haven't found any hardware Trojans in the wild, at least publicly. Various ways you can insert a hardware Trojan are at the design level, or at the manufacturing level, or afterwards. So something at the design level would be at some programmer or something gets bribed by some secret agency or something to add a few extra lines that in the like HDL source code of the chip you're designing. Or maybe at the manufacturing level, someone edits the doping level of a gate or something like that. These things can be hard to detect. You have to use things like program verification techniques and that kind of, or functional testing afterwards to determine if they've been tampered with, if you don't have good controls in place. So hardware Trojans can be used to do simple things like just decrease the lifespan of a chip by, like, say, thinning the width of a wire or something like that, really subtle. Or you can do something more devious, like have it use one of these sidechannel attacks we've been talking about to covertly transmit information beneath the radar. And you can even modify the behavior of the chip to do things like disable it on a remote command. So there's been lots of academics and stuff who have designed their own hardware Trojan proof of concepts to see how it might work, so we can make techniques to hopefully detect them. But there's a recent one where someone was able to make a hardware Trojan just by changing the doping levels at the subgate level. So they based their hardware Trojan on the actual designs of the Intel's Ivy Bridge tree random number generator. And just by reversing the polarity of a few things in there, they were able to decrease the entropy of that random number generator by a significant amount if you knew the secret of how they modified it. If you don't know the secret, then it'll pass all these statistical tests like the NIST ones, and it'll pass the functional built-in self-tests and other ways we have of detecting if there's a hardware Trojan or not. Also, one technique to detect hardware Trojans is to get a chip or some other hardware that you know for a fact isn't compromised, and then you do these various like side channel like analyses on it, and like measure its power usage and all that kind of stuff, and then you compare that with some other device that you're not sure about, and if they have different signatures on these various side channel like attack things, then you can say that the one that doesn't match your good copy, known good copy, is probably a Trojan. All right, so how do you defend against people reverse engineering your stuff? Well, the biggest way is that you make it really small, which they're doing a very good job of, which is why probably no one in here has access to any of these fancy electron microscopes or focused ion beams, that's what the fib was, on things, because they cost tons of money, way outside our reach. You have to like work at a semiconductor fault analysis lab or something like that to have access to them. So, but if you are wanting to protect your stuff from someone with that kind of power, there are some techniques you can use. Like you can put in these like meshes that have stuff flowing through them. So if you try to put a little probe into there to see, sense the currents flowing across the chip, it will be detected by these mesh, and it can activate various defenses. So other sensors you can use are measuring voltage and frequency. Those can protect against stuff like fault injection as well. And temperature and even radiation sensors. You need the radiation sensors because some of your code is, you need the radiation sensors because there's one attack where if you have some non-volatile RAM, certain kinds of it, if you just blast it with X-rays or some other high power source like that, it will cause the memory to burn in. So even if you unplug the power, you can still read it off later. So that these defenses that they have when they detect you tampering with it won't come into play. So if any of these sensors do fire off, they can activate defense mechanisms like zeroing out the memory that contains secrets like cryptographic keys that you might want to extract. And they can even do that by like activating thermite charges, which is pretty cool. All right, so now we're just going to take a little diversion here into a few odds and ends. One's quantum hacking. So quantum cryptography, otherwise known as quantum key distribution, which is a better name for it for the most part. It's a way to secure the exchange keys in a way that if anyone tries to eavesdrop on you, they will be detected. That's the idea. And the cool thing about quantum cryptography is that instead of relying on unproven mathematical assumptions, which is what public key cryptography is about, even though I'm pretty sure that no one's going to break it, but there's no proof of that, or you have someone in an armored van with a huge thing of hard drives with lots of keying material on them, and you say, take this over here. But it wouldn't be a lot cooler if you could secure your key transfers with the laws of quantum physics. It at least sounds cool, but it doesn't actually work in practice. In practice, there's a lot of things wrong with it. For instance, it uses this classical channel to exchange like post-processing information. In the security model of quantum key distribution, this classical channel needs to be authenticated, but it doesn't need to actually be encrypted. So that means if you were just trying to use it in regular mode without encrypting the classical channel, you would have lots of problems. If there was some kind of side-channel attack against the quantum key distribution hardware. I'm not really going to go into it because it's hard to explain too much, but I just want to say that there are attacks against it. So there are security proofs for quantum key distribution schemes out there that say this is secure. The problem is that they make assumptions. Some people misinterpret this to think that quantum key distribution is unconditionally secure. But if you've been listening to this talk at all, you know that your hardware can't necessarily be trusted. So even the very first quantum key distribution prototype had a really bad problem with an acoustic side channel, where the creator himself said that the prototype was unconditionally secure against any eavesdropper who happened to be deaf. Because every time it had these things that would change the polarity of a photon that comes out, which is how it worked. But every time these things changed, it would make a noise that you could differentiate between if it was shifting it in one polarity versus another. The commercial versions of this have been attacked in ways that can't be detected, and this is some recent results. These attacks often use really high-powered lasers and things to force the photon detectors that are involved in the quantum key distribution schemes to misoperate. That's a common way to attack them. Most attacks against this are against the photon detectors themselves, so there's been lots of work trying to come up with a scheme that will be resistant against side channels like this. So that's called like device-independent quantum cryptography. And the security model that lets you have one kind of hub or something like that, where even if it's controlled by the attacker, you should still be able to securely exchange keys across it, which is pretty neat. But I'm sure there'll still be lots of side channel attacks against it. But even though we've had these side channel attacks against it, because these side channel attacks rely on having access to the stuff exchanged over the classical channel, that doesn't need to be encrypted if quantum cryptography can be perfect, which it isn't. So in practice, the vendors who make these quantum key distribution systems know that they're not necessarily secure. So as a precaution, they encrypt the classical channel, which means that your eavesdropper here can't get access to the information that they need necessarily, unless they're also able to decrypt it. But in the words of one of the famous researchers who does attacks against this, quantum security isn't perfect, but security is a cat and mouse game, and with quantum key distribution, we have a bigger mouse. All right. All right, and then finally I want to talk to you about mind reading, because I think this is the most awesome thing I'm going to talk about. I'm pretty sure that the side channel attacks against your brain are going to be like the most scary things you can imagine. You don't want people reading your thoughts. Right now, that seems like science fiction still, which is a good thing, but maybe in the future that will change. So at the moment, we all know certain things about what you could call side channels against humans, like micro-expressions, where like when you're lying, you might maybe smile really fast before you put on your serious poker face and say, no, I didn't do it. And people say that they can tell if you're lying by looking at stuff like that. You also have your lie detector machines, like those EKJs that like measure your galvanic skin response, and they say that if you're stressed out, you're more likely to be lying, so you're more likely to be sweating, stuff like that. Those things are, people like to say, oh, they're not accurate or anything, but they do better than chance, which is a lot better than some of us can do at telling if someone's lying. And a more interesting thing than that is using brain-computer interfaces to infer your thoughts, like hacking them. This was research that was done like a few years ago, where they used a consumer-grade EEG. It was like a NeuroSky something or another. It cost a few $100s. They had all these college students go into this room, and they would look at like strings of numbers and stuff like that, and say this is like your bank account number. And by measuring their brain waves, there's a certain brain wave called like the P400 brain waves, something like that, that when you recognize something, it creates like a spike on the EEG measurement if you're measuring it. So by looking at when these spikes happened and comparing it to what the people were looking at, they're able to make good guesses about things like their bank PIN numbers. But these attacks are still kind of out there waiting to be discovered, and not really, I wouldn't call them practical yet. Which brings up a good question. Should you even be worried about this stuff? Is this stuff, in fact, only the domain of people who like to wear tinfoil hats and the mistaken belief that they actually do anything? or is this a real threat? I don't really know that anyone is out there doing these sorts of attacks on like consumers or anything like that, but we know that government agencies and things like that have been doing this for a long time. And when it comes to things like banking chips and stuff like that, people have done a lot of research on how you can hack them with side channel attacks. So there is a lot of concern about this stuff, but is it actually being done in the wild? Does anyone happen to know if anyone happen to have any experience about an attack like this in the wild? I didn't think so. All right, so I'm here to tell you that you should take this up as a hobby because it's actually getting cheaper to do it now. There's been a lot of people who posted videos about decapping chips in their basement, using lots of dangerous chemicals and stuff like that, how to do it affordably. I think that'd be awesome and I'd want to do it, but I don't really want to kill myself, so maybe not yet. People, like at DEF CON last year, there's someone who used a cheap, like $15 software-defined radio dongle to do this TEMPEST attack I showed you about earlier, where you reconstruct the image of a monitor with the radio waves. It was a really crappy reconstructed image, but you could still tell that it was a reconstruction with just a $15 toy, basically. There's people who have made some open source frameworks for doing these kinds of side channel attacks mostly, like one's called Giant and other was Chip Whisperer. And it's really getting to the point where this is accessible to hobbyists now, which is kind of neat. And if you want to learn more, there's going to be a Utah Sec presentation that I just got the email like a while ago that said it would include hardware hacking. Don't know what that means exactly, but that might be interesting to go to. And they have a Coursera hardware security class. Also the Cambridge Security Lab, Cambridge University. That's a really good resource. That's where a lot of material from this talk came. And if you just want a big list of academic papers, the Sidechannel Cryptanalysis Lounge is a good source for that. So, any questions? All right. That is my presentation.